All right, welcome back to System Software. So we have basically finished all of the content for all the projects, at least for the systems programming projects and the compiler project. Today I kind of left it open-ended as project review, but I have also material prepared to go over in more detail on the function translation stuff, showing you both the translation in an example and also how the assembly runs at runtime, how the stack and the state of the machine changes at runtime. But also just happy to go over whatever parts of CodeGen you'd like to go over again or have any other questions on. So I'll leave it up to you guys how to proceed. Otherwise, I have some prepared material as well. And the next time, next time was going to be this stack smashing. That was my plan. So anyway, this is going to be like an illustration of a classic attack that depends on knowledge of how the compiler implements functions using assembly. So we'll see some sort of practical illustration of that knowledge being used in an attack. And then next week was going to be the final review. Seems like most people will be here. I guess let me know if it'll be recorded as well. So all these classes will be recorded. Then we have the break, and after we come back, we'll have a final exam. So we're almost at the end of the semester. Any questions on the CodeGen stuff? Lectures from last time? Logistics? CodeGen 1, Tanan is going to grade this today, so you'll have your CodeGen 1 graded soon. He was a little busy, understandably, and we kind of lost track of this, so apologies for that. But we'll have that regraded soon. Then CodeGen 2 is due tonight, 11:59 p.m. And CodeGen is due Tuesday. But remember, you have up to 12:04, that 11:59 to submit all your projects. And even if you haven't submitted it yet, you can still submit late on this date. All right, any questions on the remaining couple weeks of class? Projects? Yeah.
If I can ask for CodeGen phrases, because it's confusing me. For enter parameters, where are we supposed to get the variable name parameter from?
You mean where are you supposed to get these parameter names from?
No, so after those parameter names, when you have to move the, trying to think of how to explain it, so I'm not great at it. After those, after that set of instructions down at the bottom, there's two more move instructions.
These?
Yeah.
Okay, so the way parameter passing works, let me get this diagram up as well for this. So this was a function that passes parameters A, B, C, D, E, F, G, and H. The first 6 parameters are passed via registers, and these are, I've given you a list that hard codes the order of the registers to pass the first 6 parameters in. And then after the first 6 parameters, you push them onto the stack. So that's what these are for entering the parameters. Sorry, not for calling the function, right? For getting the parameters. So the caller is supposed to have already copied the first 6 parameters to the registers and then pushed the any remaining parameters onto the stack. So this is what your stack should look like, where the 7th parameter is RBP plus 16, 8th is RBP plus 24, 9th, RBP, etc. So what this code does is it takes each of the parameters, the first 6 of which can be found in those 6 registers. That make sense? So that's why we have move instructions from these 6 registers. And then the rest of and those are moved into whatever the offset for the parameters are. So in this function, the parameters are passed in this order. So it's the same as this diagram. Parameters are passed in this order. So the first parameter goes to wherever A is from the symbol table. The second parameter goes to wherever B is, looking up the offset in the symbol table, and so on. When we get to the seventh and beyond parameters, those the destination is the same. The destination is these parameters G and H, but the source of those variables is no longer in a register. These are in the stack, and we can access those by offsets from RBP, starting from plus 16. So that's why we have a load from the stack into a register, and then that register into the variable, because in the Intel architecture, we can only do a single load or store per instruction. So this is the same kind of code you see for doing an assignment, where you copy a value between two memory locations. So this is copying from plus 16 RBP, which is here, so RBP plus 16, copying that into the local variable offset for G. And similarly here, we're copying the stack parameter H, which is RBP plus 24, copying that into the local variable location for H. Does that clear things up? So yeah, that's where these come from. So the only kind of programming nuance you'll need to deal with is looping over all of the formal parameters. So that's the name of that's how we call the parameters of a function. We call them the formal parameters. Those are the ones that are named. So this is the list of the formal parameters. This is how you loop over them. And so you just need to loop over the list, and for the first 6, you generate this code using the list of parameters. So you just loop over in the first 6. You can write this in multiple ways. You could either loop from 0 to 6 exclusive, and then also simultaneously loop over this list and generate this code, and then loop from 6 or 7 to 7 exclusive, then loop from 7 to the end of the parameter list to get the rest. Or you could have one loop, and inside just check I. If I is less than or equal to 6, use registers to get the parameters. If it's greater than 6, then generate these RBP offsets into the parameter stack.
Okay.
That's the only nuance here. And so so this text here just explains that same thing. But yeah, it's just, this is the loop. I've given you the loop for this. So just loop over it, check whether you're up to parameter 6. This 6, so 0 to 5, because this is going to go from 0 to 5. So 6 exclusive, because that's index 6 is argument 7. Other questions on CoGen 3? Parameter passing? CoGen 2, just due tonight? Okay, all right. Let's do homework. So the homework, so this is what I have prepared for the class as well. So I won't go into great detail on these because I have an example laid out already, a slightly different example. Questions on, specific questions on this problem. Like, what are the stack frames, return address, old base pointer, local variables? Any questions on how to do this, the stack frame? So this, you don't even need to generate the assembly code. You can just draw the stack frames for this. Do you want me to show the stack frame for this? All right, let me show the stack frames for these. So oops. All right, let's put homework 24 here. Okay, so we'll just assume we already have the stack frame created for the execution of whatever calls main. But when we call main, main is going to have, let me do it this way. So when main gets called, there's going to be a return address for whatever calls main. And I didn't go over too much this like boundary condition, but if you remember, there's this entry point to the program, that underscore start that the loader invokes. In there, the C runtime is what actually calls the main function. So main actually can return to the C runtime. But I didn't go into too much detail on this. But if you didn't include the return address for the main stack frame, that's okay. But this is the return address for the caller of main. So this section here, this is main's stack frame. And then underneath of main, and in the project I gave you, there's also like a register you have to save. There's going to be alignment requirements for x86, but don't worry about any of that for the homework. I just wanted to make sure you show return address, old base pointer, and local variables. There will also be an old base pointer for the caller of main. But again, if you didn't include this, that's okay. And then we have the local variables for main. So the local variables will be recorded on the stack for main as offsets from RBP. So RBP will be pointing here. It'll be pointing to the stack element that has the old base pointer. That's just the design of the calling convention for x86, 64, System 5. And it's normally like this because then you have this linked list of stack frames, is what this RBP pointer creates. Okay, so this is the state of the stack when main is called. That's when main is entered. So then so any questions on this setup so far? All good? Okay. So then when x equals 2 is called, the memory location associated with x, the stack frame entry for x, will be populated with 2 in our compiler scheme. Then retval will be populated with whatever the return value of f is. So how do we know what the return value of f is? Well, we have to run the call. And how do we execute a call? How does the stack frame change when we have a call? What gets put onto the stack when we have a function call? So we have some pointers here about what to include. So there's no, there are parameters here. I forgot to include a parameter. Okay, I think I was supposed to make this x, so apologies for that confusion. Don't worry about it if you didn't get it. So this would have been a local variable x here, the local variable for the call to f. Don't worry about it, I omitted it accidentally. So there would have been, sorry, it's not going to be on the stack. It's going to be on it's going to be via a register. But don't worry about this if you didn't include this. So it'll be passed via register, and then the stack frame for f will be constructed starting with the caller. So the caller will save the return address. So this is the return address into main. And then what gets saved onto the stack by the callee. Once we have the return address saved, we do the assembly call, and we go to the callee, f here. What gets pushed onto the stack next in our calling convention? What's that? Yeah, the old base pointer. So the old base pointer, this current base pointer points to main stack frame. And then the old base pointer is pushed, and RBP is updated to point to the new stack frame. And you didn't have to draw it like this, but you can think of this as a linked list of stack frame like structs. So this old RBP, this is in my way, so I'm going to move it. This old RBP, you can think of it as a pointer to the caller's stack frame. So that's the new RBP, and then local variables get pushed. So here we have one local variable, also called x in this function. But you can see it's a different place in the stack, it's a different variable. And it's gonna be set to, yeah, so this is our stack frame setup when we call f. Questions about this? So then here we assign x to 3. Which x gets assigned? Well, it's the x in the current stack frame, f's current stack frame. So it gets assigned here to 3. And now we return. We start tearing down the stack. So the return value goes into RAX. I know I didn't ask for this in the homework, but the return value gets passed via RAX. And then the stack frame gets started to get torn down. So the local variables get popped off, the old RBP gets popped off, and the RBP register gets updated to point to the caller's stack frame. And then finally the return address is popped off and flow of control is returned to this point in the calling program. At which point we can now take the return value, which is stored in RAX, and use it to assign to redval. Questions on this? And then finally we return x, so x here has value 2, so RAX is going to be set to 2. And then we have our return, so the return, before we do the return, it's going to tear down the stack frame by removing local variables. It's going to pop the old base pointer and update it. It's going to be somewhere up here in the stack above main, so there's going to be like an entry point function here. And again, I didn't show you the details of this. This is in some library code that is used to set up the C runtime. And you don't have to worry about it too much in writing the compiler. It's like set up for you. And then the return value is, return address is popped, and we return to whatever called main, which is, in our case, the C runtime. Questions on stack frame, what the stack frame looks like during function calls? Okay, and as usual, I put all these diagrams up on the website as well, so you can always get them from there. All right, write move instruction that implements x equals 2 above in function f. So what does the move instruction look like for, and it could be multiple instructions. So let's, yeah, so what did someone write for this? So what's the move instruction look like for x equals 2 above here? So this is question 1. This is question 2. Any takers? Yeah. Okay. Move immediate, value 2. Percent. Yeah, you can use percent RAX. Actually, it doesn't matter, which almost doesn't matter. You can use any of the general purpose registers. So yeah, let's move into RAX. What was that? So it'll be an offset from RBP. And here, depending on how your stack was set up, in this case, assuming all the variables are 64-bit, this is where RBP points to. So this will be an offset of -8, -16. Now in our compiler, the code I gave you also basically pushes the RBX register, pushes that register. This is just the calling convention. Depending on who designed the calling convention, some registers are required to be saved by the caller, some are required to be saved by the callee. They're called scratch registers. So it's just a trade-off between how many registers are left available for the callee to use from the caller. So there's just design trade-off there. It differs for even Windows versus Linux, the callee, caller, saved registers differ. It's just a thing you have to read the reference for. Here we don't have that, so the offset would be -16 for X here. This is -8, this is -16. And yeah, so that's it. That would move 2 into the memory location associated with X. Questions on that? Okay. Question 3, in the x86, 64, System 5 ABI, how are parameters passed? So how do we pass parameters in our calling convention? So this was shown in this was illustrated here. It's also described in the notes. First 6 are passed to these 6 registers, and the remaining are pushed onto the stack. That's the calling convention. So there's a nice page if you're interested in learning a little bit more about these calling conventions. You can see that depending on the architecture and depending on the operating system, there are different calling conventions. So for System 5, which is what Linux and lots of Unix systems use, they actually have different calling conventions compared to if you're running a Microsoft C program on a Microsoft OS. So you can see that the parameter registers are even different. So in the System 5 ABI, we have the first 6 being passed. In the Microsoft ABI, only the first 4, and the rest are pushed onto the stack. So these are just conventions. And if you're writing your own software and you're writing your own compiler and you don't want to interoperate with other C code, you don't even have to follow these conventions. You can design your function call however you like. You can save no parameters. You can use all stack for doing it. And these stack, scratch, and preserve registers, these are the callee and caller preserved registers. So it just so happens that RBX has to be saved by the callee. But again, these are just conventions. If you want to read a little bit more about how systems implement these, how systems define these conventions, you can check this out. But you can just see that this is just a human-defined convention, that if you want to interoperate with other code written with these conventions, you have to follow those conventions. That's all it really means. And so the compiler you write, I have you follow the System 5 conventions so that your code can be called by C. It can be called by the C runtime. You can have a main function that's called the same way that a C main function is called, and you can also call C functions. And you can write C programs to call you. So that's how iolib.c, if you ever wondered why we link with iolib.c, you can actually just call C functions because your compiler is following these conventions when it generates assembly code. But anyway, this is all kind of pretty low-level, nitty-gritty detail that you don't have to worry about too much, just sort of be aware that it's there. All right, other questions on number 3? Yeah.
So the correct answer was the RDI or that?
Yeah, well, so yeah, it's the correct answer is the first 6 are passed via these 6 registers, and the remaining are pushed onto the stack. That's the answer. If you listed out the exact registers, great. If you just said registers, that's fine. If you said 6 on registers, 7 on stack, or the remaining on stack, that's fine. But just understanding that there is this calling convention. And you can even see that for the older 32-bit systems, they had no parameter registers, just onto the stack. So when I wrote compiler stuff in class when I was in grad school, it was 32-bit, just to show how old I am. And we didn't have to push anything onto the stack. It was a lot easier. It's kind of a pain to deal with the registers, but I tried to make that a little easier for you with the given code. All right, other questions on number 3, the ABI? And then finally, we have the contents of a stack frame. Which ones are caller created and which ones are callee created in our conventions? So parameters, stack parameters. Who pushes those onto the stack? Is it the calling function, the caller, the function that makes the call, or is it the callee, the function being called? What's that? The caller, right? And this makes sense because it's the caller that has access to those values. So you're usually passing local variables or some expression of local variables, the caller has access to that data, so it pushes that onto the stack before making the branch to the callee. Okay, return address. This is kind of a subtle one, but who saves the return address? Is it the caller or the callee? Say it? Just yell it out. Caller, right, caller. Again, because if we already branched to this code, we've already lost the return address. If we just branch and we haven't saved the return address, we don't know how to get back to this function. Because branch is just one direction. Once you branch, program counter is updated. So the caller saves the return address. And in the x86 world, the call opcode will both save the return address by pushing it and do the branch. Okay, local variables, who pushes those onto the stack? Callee. And old base pointer, who pushes those onto the stack? Again, callee. All right, good. Any questions on this homework? Hopefully that clears up. I know there's a lot of sort of technical nitty-gritty to this like calling convention stuff, and you have to use it if you want to interoperate with this code. But I'm trying to kind of insulate you from those details and just give you like what to do so that your code will work. But just understand you just need to understand that there is this calling convention, that there is this simulation of functions at the machine level, and then next time when we look at the stack smashing attack, we'll see how attackers exploited these conventions in order to basically have remote code execution to take over control of systems. Okay, let's take attendance. Okay, so yeah, today, as I said, is a fairly open-ended review of the compiler project, because I know it can be a complicated project to do, but I also have some prepared stuff, because I think functions are the hardest, so I prepared some detailed translations and execution of the function stuff. So what someone actually asked in office hours is they sort of thought the project was maybe too easy and too hard, because if you look at the final code, most of it is just printing stuff out. And so if it's that's okay. It really is. The hard part in compilers is not just printing out code. It's easy to write code that prints out code, as you might have noticed, right? You just literally print out strings, and you're doing code generation. You're doing this fancy sounding thing. All the challenge in it is getting it to be correct, getting it to match the actual input. And that can be really subtle and difficult to do. You're basically writing a translator. But I've tried to make it the easy mode, paint by numbers compiler, where you have a single template for each construct. And as long as you sort of follow that template, you should be okay. So if you notice that the functions are not that complicated, there's a little looping when you deal with parameters, but that's basically it. Otherwise, it really is just kind of templates, printed out templates. So yeah, that was a good insight that one of the students pointed out. So questions on any part of the compiler project? Everybody's good on the compiler project. Okay. Yeah.
So I just have a second for Gen 2.
Yeah.
Is it possible to get clarification on when to use the operand number and when to use the variable?
Okay, let's see. So let's take a look at the actual, when to use the operand versus variable. So and this is the way I designed the grammar, but so there's no like law of nature here. But you can follow the convention in enter assign and enter operation. So the way I wrote and actually this doesn't really reveal it well. Let me go to enter operation. Yeah, so enter operation is the pattern kind of I use for this grammar. And this is no law of nature. I designed it this way. So whenever I have the variable keyword, I mean the destination, the thing on the left-hand side of the equal sign. And operand is on the right-hand side. That's the convention I used. So if we look at the full grammar, so here's the full grammar. You can see this pattern repeated in all of the variations of assignment. So here we have assign. The left-hand side is called variable, and the right-hand side is called operand. Same with dereference. Operand is the thing on the right-hand side. So what might be, I guess, a little confusing is that here for assigned dereference, I still call the left-hand side variable. You might rightly say this is actually like an operand, but I didn't do that. I just use whatever's on the left-hand side. I call the destination-like thing. So for this case, it's not really the destination, it's the variable that holds the address, which is the destination. But yeah, so the rule of thumb that I use, and again, just a convention I used here, left-hand side is variable, right-hand side is operand. And I repeat this convention for all of the assignments. So you can basically guarantee that for anything that has an assignment, including the call, the left-hand side of the assignment is called variable in my grammar. Okay, hope that helps. But yeah, again, I was trying to make this stuff somewhat easy. And again, and also Antler is like an awesome parsing framework. It allows you to name these things. Otherwise, you'd have to say like name 1, name 2, name 3, or name 0, name 1, name 2, which are, it's kind of annoying, but you can name them. And so I gave them names that I hoped were sort of patterned like, yeah.
Was this file available to us, or am I just being stupid?
Oh, it is. Yeah, so I think I showed it in the lecture notes, and it's also just part of your project, part of that starter code you downloaded. Sorry if that wasn't completely clear, but it is, it's the grammar. I may have said it really quickly in passing or not said it at all, but it's in here in the compiler project overview. It's this simple IR grammar here. This is the grammar. It's the same as this one. But this is in your code base necessarily. Well, not necessarily, but I could have given you the generated parser. But this is what the Antler tool consumes as input. So the Antler tool is another kind of compiler. It takes in this grammar definition and it generates C++ code. So it literally takes this in and generates this C++ program to actually do the parsing. So if remember when we talked about grammars and parsing, writing parsing code is tricky and long, and this is what the parser's code looks like. It's like 1,400 lines of code. That 1,400 lines of code is like fully defined in this 50 or so line grammar, which defines what the grammar looks like, and then a parser can be generated from it. Yeah?
So I have a question. In CodeGen 3, in the section going over how to implement Interpol, it says we're using Python code. Is it supposed to say C++? Or are we actually using Python?
Oh, it says Python. No, it's supposed to say C++. This is like, sorry, this is stale stuff I had in there. I originally had this for a grad class where we actually did use Python.
Oh, okay.
But apologies for that stale code there. Let me make sure. Oh yeah. I'll change that. I changed that to C++. Sorry about that. Yes, it is not Python. But Antler supports generating Python, C++, Java, several other languages. So someone in here may find themselves in their career where they need to do language parsing of some kind. And Antler is a great option for doing this. It's very easy to use compared to like previous compiler toolkits. Other questions, general questions on the project? CodeGen 1, CodeGen 2, CodeGen 3? Okay, so let me go over CodeGen 3. Let me go over a pretty detailed example of generating code for CodeGen 3. And this is the example from this CodeGen handbook. So in the last section here on function parameters and calls, there's like the examples of entire function call code generation. It's a little tough to read, but you can actually like run these and compare your output with this given output, both for a simple example with a single parameter, but also a 8 parameter example, which will have both registers and stack. So these are the register parameter passing. This is the stack parameter passing. So I'll have both of those. But anyway, I took the simple one here, the one with the single parameter being passed, and I turned it into a pretty detailed example. Okay, so we've got two functions, main, and so main just has two local variables, ret val and x. It assigns x to 3, and then it calls function called func, passing x. And then finally it returns whatever that ret val was. Questions on that simple IR program? So that's all it does. Just sets a variable, makes a function call, saves that return value. And here is the code for func. So all function it does is it just takes a single parameter a and then returns it. Identity function, I guess you could call it. Questions on that, those two functions? Okay, so here is assembly code that is equivalent to this simple IR. So now note that your assembly code could look different if you made different decisions. There's, as you know from programming, there are many, many ways to write the same program. There are many, many ways to write the same program as in equivalent programs that have the same inputs and outputs. But if you follow the templates I showed in class and in the CodeGen manual, you may get the exact identical assembly code. Okay, so and the way I kind of designed this compiler is that each one of these lines of simple IR is a statement in, or is a construct in the ANTLR grammar. And the ANTLR parser framework will automatically walk the tree for you. And whenever it sees one of these lines, it'll trigger that enter function, like enter function, enter local variables, enter assign, etc. So here, let's look at what gets generated by a correctly implemented compiler when the ANTLR parser seeds each one of these constructs, and your implementation of the compiler generates code for each of these constructs. Okay, so the function main statement is like a single ANTLR construct, a single construct in our grammar, and it generates both the label. It also generates that assembly. I left out a little bit of the assembly code for space. These pseudo ops. These pseudo ops are also being generated by your compiler. I left them out here just to save a little space, but technically it'll be all of this that'll be generated by enter function. Enter unit will generate this. Enter function will generate this. So this function main will generate this assembly code. Questions on this? And so note, the only thing that actually changes between different simple IR programs is this main name of the target. This code is like boilerplate. This is called the function prologue, and it's the same for every function that gets called. Questions on this so far? Everybody go to this? Okay, so local variables, this is code I gave to you. All local variables does for code generation is it spits out an instruction to allocate space on the stack for all the local variables. Internally in the compiler, it also generates the symbol table so that you have a way to keep track of which offsets each variable has. And one of the reasons I wrote this for you is that there's a lot of annoyance in generating the right offset or the right allocation for RSP. In the Intel x86 System 5 ABI, you have to align things at like 16-byte boundaries, and it's very annoying to get right. So that's why you'll notice that this may be larger than the number of variables you have. Like for instance, here we only have 2 variables, but I'm allocating, that's right. This one is already 16-byte aligned, but if you had 3 variables, you'd allocate space, that looks like 4 variables. But anyway, don't worry about that too much. I've generated this code for you. So you just call my version of enter, you implement my version of enter local variables, and it'll generate this subtraction. So subtracting from the stack pointer is equivalent to saying push over and over and over again for each variable slot. Questions on this? On this so far? Okay, and then here's our assignment statement. We saw this several weeks ago. that corresponds to this assembly code. So just like we saw for the homework, one way to generate assembly code to do this is to do an immediate store of our value of our number into a register, and then store that register into the memory location associated with X. So hopefully that looks familiar. All right, now the slightly more complicated one here, which is for CodeGen 3, is the call. So the call actually corresponds to all of this assembly code. So it's not just the call. It also involves the parameter passing, as well as any cleanup of the stack and saving the return address. So let me go through these one by one. So the first thing that needs to happen, because remember the caller sets up the parameters. In this case, how many parameters are being pushed onto the stack for this function call? What's that? How many are being pushed onto the stack? So one parameter is being pushed, but how's it being passed? What's that? Through a register, yeah. So remember, for this ABI, the first 6 parameters go through registers. So this move instruction here, this is passing via register. And again, this is just the calling convention, so we can interoperate with other C code on our system. But because we only have one parameter, we only generate a single move that copies whatever the value of X is. So this is X, this first thing is X. And this is the register for the first parameter for passing the parameter.
So none on the stack?
So none, yeah, exactly, yeah. So none on the stack. That was my little trick question. So no parameters have been passed onto the stack here. So the stack has not changed before we make this function call. And so you can see after the function call, I have an add 0 to RSP, which seems kind of pointless because it doesn't actually change the state of the machine. I do this because I don't want to have to write code in my compiler checking for whether I need to tear down the stack or not. So if I did have parameters on the stack, and let me show you an example of that. In this program I have 8 parameters. So the first 6 go via registers. The last 2 are going to go on the stack. That's just the calling convention. So in that case, the generated code has a lot more parameter passing stuff going on. So we've got the first 6. So I do them backwards here because I think it's easier to generate. So these are the last 2 parameters being pushed onto the stack. So this is G and H. So if you were to actually look at the symbol table generation for these parameters, for these local variables, they'd be G and H would have these offsets. But remember, that's all computed for you. You just in your compiler, you just ask the symbol table for the offset. But as you're going through the parameters of the call, you loop over the parameters of the call. And for the first 6, you pass them by moving to the 6 corresponding parameter registers. And any ones after 6, you just generate push statements for. Yeah.
Why did you add 0 to RSP?
Oh, yeah. So, yeah, let me get to that. So you see here in this case, I add 16 to RSP.
Oh, okay.
So that's because I've pushed 2 8-byte parameters.
Allocating the space.
So to undo, exactly, allocating the space on the stack.
Free.
Oh, yeah. So push allocate, yeah, right. Push allocates them, add, slightly confusingly freeze them. And the reason it's add is because the stack grows downward. So whenever you push, addresses become negative. Addresses go lower. So adding actually pops things from the stack. So pop and add 8 bytes are equivalent. Pop 1 64-bit add value, and add 8 bytes are the same operation in this machine. So you could certainly have generated multiple pop commands here. The reason I do it with this number is that I've given you, if you look in the handbook, I've given you a number that you can just use to tear down the stack. Oops. It's in here somewhere. Yeah, it's in here. Sorry. So yeah, it's described. I can't remember exactly what it's described. Oh no, wait. Sorry, no. That's not stack offset. That's different. Sorry. I was confusing this with the function protocol. So you'll need to count up how many variables are on the stack. So you could either generate multiple pop statements, or you just count how many parameters are on the stack, multiply by 8. So if 2 parameters are on the stack, you multiply by 8, and you've got add 16. You could also count up how many parameters there are and just generate pop statements. That'd be an alternative way to do this. So yeah, it's described here. Generate instruction to remove any parameters on the stack. So how do we know how much space we use on the stack? You just count up how many parameters were pushed onto the stack, multiply by 8. Does that make sense? Questions on that? So that's how, yeah, so for this example, so sorry, I'm switching up between examples. Our original example, we had no parameters on the stack, so I just add 0. Now this is the same reason that I do things like move immediate to a register first. By generating it this way, by allowing for 0, my enter call function is much simpler. I just always generate an add, and then whatever the value, whatever the number of parameters there are, if there's 0, it's still valid to say add 0. I don't have to check whether it's 0 or not. I just write out however many parameters there are, even if it's 0, and then my code will still be correct. And it's just easier to write the compiler this way. That makes sense. Okay, so that's 2 parts of the call. We have the parameter passing. In this case, we have no stack parameters, but if there were, you would just see if you're beyond 6 parameters and then just call push instead of move to a register, because you're out of registers. You only have 6 registers. And then you just generate the call. The call is really easy. It's just call plus whatever name of the function was given. Now notice here that if somebody wrote call, like if you didn't link these 2 programs together or you put the wrong name, the compiler will still generate code. And then when you go to run it or link it, when you go to link it, the linker will be like, hey, I don't know about this function. I mean, you might have seen that when you tried to compile your programs. But the compiler doesn't actually have to care whether this function exists, how many parameters it has. All it has to do is just do what you asked, which is just pass these parameters via the convention and branch to this label. That's all the call function does. It doesn't need to know anything about the actual implementation of the function. So that's the call. And then finally we have the, so any questions on that? Any questions on the call and the parameter passing? Okay. So then the last step is to save the return value. So unlike C, in C you can have void functions that don't return anything. You can also make function calls to and not save the return values. To make it a simpler language to compile, I just always expect a return value. And because the return value is expected to be passed via RAX, the return just always copies RAX into whatever variable is given on the left-hand side. Even if your function doesn't actually return anything. It's just going to give whatever happens to be in RAX, even if your function doesn't correctly return anything. And it's the same behavior in C. Questions on this so far? So that's probably one of the more complicated parts is getting this right, particularly the parameters and stack versus register parameters and getting this tearing down the stack correctly. That's hard to get right, and it's hard to debug too, unless you use the GDB debugger or use another debugger to actually inspect the stack. So you can actually see the stack pointer and just make sure it gets, the RSP before the call and after the call. You want to just make sure they're the same to make sure you didn't mess up your stack. Questions on this? Okay, so then the return is really easy from our function. It's just copying, not this again. It's just copying whatever variable is given in the return or immediate value to RAX. That's all the return corresponds to. So notice that, and this is true in C as well, the return statement doesn't actually branch. It doesn't actually go back or return to the caller. It's really just saving the value in RAX, and then it's the epilogue, the last part of the function, that ends with return. Because what would happen if we just returned immediately right here? What would happen if we just said return right here whenever we call a return instruction? What would happen to our stack? So this code wouldn't get executed. So all the stuff we pushed onto the stack to construct the stack frame here, that would remain on the stack. And in fact, we wouldn't have a return address on the stack. We'd have some data. We'd have our local variable. We try to return to whatever our data happens to be pointing to. So the return instruction, and this is similar in C to a degree, the return instruction doesn't literally branch back to the caller. It has to first tear down the stack frame before it can return. And so we can see here our end function. So this is the way I designed our language, just to make it easy to generate this. It's the end function statement that actually does the stack frame teardown. So first thing it does is it removes local variables. And so that corresponds to here. So you can see, it's a stack, first in, first out. So the local variables get popped. So they were pushed here via subtract of the stack pointer. This is inverted. You can see this is like the literal opposite of the local variable being pushed. We pop RBX off the stack. So that's the next thing we did before we made local variables, the previous thing we did. And then we restore the base pointer. So that undoes this code here. So the pop updates the RSP, which undoes this part, and it saves whatever the value on the stack into RBP, which undoes the change to RBP. So yeah, question?
No.
Oh, okay. So yeah, you can see this symmetrical pattern here. It's just we build up the stack. I had a stack described here. We build up the stack, and then we tear it down in reverse order at the end of this function. So this is the prologue. This is the function epilogue, and they're like duals of each other. They're like inverses of each other. And that ensures that once we return to the caller, that the stack is in the exact same state that we left it when we made the call. Yeah?
There's no situation where we end the function, we want to keep things in stack.
Ooh, that's a really good question. So in this language, no, but there are such languages. There are languages that, there are languages called functional languages. And if you take programming languages or look at some Python stuff, so that is a very interesting question. There are languages where, so these languages, you can actually return functions themselves as if they were values. So you could define a function inside of another function and then return that function as if it's a value. And there's a technique called a closure where all of the local variables of that function are still active, even though you've popped the stack. And so these compilers use special techniques to hold on to those. One technique is to save them onto the heap instead of the stack. But yeah, that's an interesting question.
So we always want to...
In this language, we clean them up. So in this language, like C, when you allocate local variables, they're always torn down when the function returns. But in functional languages, that assumption is not true anymore because functions can be passed around as variables, as if they are variables. So if you've ever had to deal with function pointers, this is maybe this is a topic, probably an unusual topic that you wouldn't have to deal with in class. But C has something like functions as values. You can actually pass the return address, pass the address of the function itself. So that would be the address of this main. You could pass that around, but you wouldn't save the local variables. In functional languages, the local variables are actually saved and passed around with the function. They're called closures. And then yes, this technique will not work anymore. You cannot just tear down you can't assume that you can just tear down the
You have
variables.
to save it so that you can then tear down, or?
So one technique is to save it to a heap, return the function pointer bundled with a pointer to its heap allocated variables, and then tear down whatever is local. But I mean, you're not going to have local variables anymore unless you on the stack, unless you can prove that you won't need those anymore, basically. But yeah, it's an interesting question. Yeah, if you look into functional programming, functional languages, Python is a good way to like get into that because it supports passing around functions. You could make a lambda. So I'm just going to give you keywords. This isn't on the test or anything. But if you go into Python and look up lambda functions, you can construct a function on the fly without a name, save it to a variable, and pass it around just like it's a piece of data. And then you can actually call it later. It's a very cool technique, very useful techniques in programming. But check it out, lambdas, functional programming. You can do it in Python. There's also full languages that are designed around this technique, which you can learn about in programming languages. But yeah, interesting, subtle question. What if you want to save these values? This language is designed, just like C, to never allow that. To always assume that once the function is over, the scope of those variables is gone, never to be run again, and so the compiler can safely tear those down. But there are languages, functional languages that but do not make that assumption and allow for different programming techniques. But yeah, interesting question. Okay, so once we've torn down the stack, then we do a return. Return is going to pop off the last part of the call, or actually it's going to pop off the last part of the callee saved stack. It's going to pop off the return address and then branch to it, returning to the caller. And because we tore down the stack the same way that we built it up, the stack isn't going to be in the exact same state that we left it when we called the function. Oh, I better move on. All right, questions about this? So the other function is really similar. I'm just going to highlight what they are. It's virtually identical except for saving the parameter. So here we have the function prologue, we have the local variable allocation, and the only difference here is that this function has parameters. This function actually has parameters, and why? This is the strangest bug. Give me 1 second. Okay, that's very strange, but okay. All right, so here's the parameter. So it takes the register that the parameter is being passed in, and it saves it to the corresponding local variable for A. So if this was on the stack, it would just move it from RBP to a register and then move that into the stack here. But otherwise, everything else is the same. End function is the same. All right, questions on translation of that? It's identical except for we have parameters being passed into the function. Okay, so those are the two functions. Let me walk through in the last couple minutes. We have how the stack actually changes when and I'm going to go through this a little quickly, but I'm recording it, so you can review it. So this is the start of our stack before we call main. So there's an entry point to the program from the loader. That's the start. This is where RBP and RSP are. RBP is pointing to this entry point stack frame. So when we call main, what happens? We first push RBP, so we save the old base pointer here. And then we overwrite, and that updates our SP to be pointing here to the top of the stack. We update the base pointer to be the same thing as where the stack pointer is. And then we push RBX. So in our real compiler, I have you push RBX for that calling convention. That's going to save whatever RBX is in here and update the stack pointer. And then we're going to do our local variable allocation. So subtract 24 from RSP. So that's going to be 8, 16, 24. So that's where our RSP is going to be updated to, and we run this subtract. And that's going to, even though it's not nowhere in the actual architecture, that's going to give us space for our local variables. What were they called? I forgot what they were called. Ret, val, and x. So it's going to give us space for ret, val, and x. This extra space is because of that 16-byte requirement, 16-byte padding requirement. Don't worry about that, just to use my local variables function and it'll handle that for you. And here's our, okay, so that's our prologue and setting up the local variables. This is our assignment from 3 to our variable x, right? This is variable x is negative 24 from RBP. So so first RAX is going to be set to 3, and then that 3 is going to be saved into x's memory location. And then here's our function call. So we take whatever x was, so remember this variable is x, this is x, and we save it into the first parameter register. So whatever x is, we save it into the first parameter register. And then we make the function call. So what is the function call going to do? It's going to so the function call will save the return address. So here, the stack pointer is going to be updated, and then the return address to main is going to be saved on the stack. And then we branch to func. That's what the call instruction does. So we've left off here. So here was our last instruction. This is our return address here. It's the next instruction after the call. The call saves the return address and then branches to func. Func does the same stuff in its prologue that main did. It first pushes RBP, the old RBP, updating the stack pointer, and then updates the actual RBP register so that it no longer points to the caller's stack frame. And then for our calling convention, we save RBX. That's going to update the stack pointer. And we subtract 8 for our local variable, which is also called x here. So subtract 8 from our stack pointer, and that's for our local variable x. We copy the parameter register into, this is x here, this is x. So we copy the parameter into x, and then we just immediately return it. So return it by copying whatever x is into RAX. RAX already happens to have this. We tear down the stack, so we add 8 to RSP. That's going to put us back here. We pop RBX. That's going to put the stack pointer back here. And then we pop RBP. That's going to restore RBP to the old RBP, the old stack frame, which is here, and move the stack pointer here. Finally, when we call return, that's going to pop this return address, which remember, left off the next instruction in func. It's going to pop that off the stack. Popping off the stack is really just moving the RSP down. And then we're going to continue running here. So we're going to add 0 to RSP. That does nothing because we haven't pushed any stack parameters. We're going to save the return value into retval. The return value is 3. Actually, I think I got the numbers wrong. But anyway, return value is, let's say it's 3 here. It's going to save it here. Oh no. It's going to save the return value, and then we're going to tear down the stack. So that's going to pop all of these elements off the stack. So these are going to be popped off the stack. RSP is going to be updated. Then we're going to pop RBX. That's going to move RSP here, popping off RBX. We're going to pop off the old RBP. So that's going to pop this off the stack and move RSP back here. And then finally, then we're going to return to the start code, and we're outside of the main function now. So sorry that was a little long, and we're 2 minutes over. I went through that a little quickly, but it is recorded. But that's the whole operation of the function call between two functions. All right, everyone. See you on Thursday.